All right, let's dive into some of the incredible math that secretly runs our entire digital world. Today, we are talking about subspace codes. I mean, have you ever really thought about it? You send an email, you stream a movie. How does all that information make it from one side of the world to the other, perfectly intact, through a system that is just fundamentally messy and noisy?
Well, the answer isn't what you'd expect. It's not about wrapping your data in some perfect protective bubble. It's kind of the opposite. The trick is to actually embrace the chaos, using a piece of mathematics that is just so elegant and incredibly powerful.
Okay, so to really get why this solution is so brilliant, we first have to appreciate the problem itself. And this problem is baked right into the DNA of the internet. You see, the internet is what we call a packet network. Your message, a photo, a document, whatever, gets sliced and diced into these tiny little pieces called packets. These packets then travel all on their own, and they can get lost, they can get corrupted by noise, or they might even show up in the wrong order. It's a super efficient way to do things, but man, it is also a recipe for disaster. So to fight all this chaos, some very smart engineers and mathematicians came up with a pretty radical idea. What if, instead of trying to protect the data, we actually made it even more chaotic, on purpose? This wild idea is a technique called random linear network coding. The core concept is, instead of trying to protect every single little packet, the network just mixes them all up. Seriously, think of it like you're making a smoothie out of your data. So the receiver doesn't get your original separate packets. They get these new blended up versions. Now here's the magic. As long as they get enough of these unique combinations, they can use some clever math to perfectly reconstruct the entire original message. It's amazingly efficient, but it also creates a brand new problem. And it's a really good question. You know, traditional error correction is designed to spot a single wrong bit in a specific packet. But what happens when the packets you're receiving are supposed to be a jumbled mess? How on earth can you spot an error in a smoothie? And this is where we get to the big breakthrough. To solve this new kind of problem, you have to completely rethink what a code even is. You have to make a jump from coding with simple points to coding with entire shapes. Let's just back up for a second. In classic coding theory, a code word is like a single point in a huge mathematical space. It's a very specific sequence of ones and zeros. If an error happens, that point gets nudged to a different spot, and the receiver's job is to figure out which original point it was closest to. And this slide right here shows the huge shift in thinking. The old way used individual, distinct points. The new way uses entire spaces. Instead of one single vector, a subspace code uses a whole vector space. That could be a line, a plane, or even some higher dimensional shape you can't even picture.
The researchers who pioneered this literally described it as moving beyond single vectors. That is a fundamental leap. It's not about sending specific points anymore. It's about sending the rules that define an entire shape.
Okay, let me give you an analogy to make this crystal clear. Imagine your data is an exact GPS coordinate on a map. That's a traditional code. It's one single precise point. But if there's a tiny bit of static or error in the signal, your GPS might suddenly point you to the middle of a lake just a few feet away. You're lost. Now, a subspace code is completely different. It isn't a single point. It's the entire country on that map. Let's say the code word is France. A small error might shift your location from Paris to Lyon, but hey, you are still unmistakably in France. The code word, the message, is the whole country, which makes it way, way more robust. Of course, the whole trick to making this work is that the countries, the vector spaces, have to be very distinct from each other. You need to make sure they're well separated so that a small error can't accidentally push you from France into Germany. The math makes sure of that. And I want to be clear, this isn't just some neat analogy. This is a real, fully fledged field of mathematics. And it comes with its own set of tools and rules for designing these incredibly powerful codes. So, inside this toolkit, mathematicians have all sorts of things. They have metrics, which are basically rulers for measuring the separation between shapes. They have bounds and constructions, which are like blueprints for building effective codes. And there's a very popular approach called constant dimension codes, which really just means all your countries are the same size. The whole thing is built on the super solid foundations of linear algebra and finite fields. Okay, so let's bring this all back down to Earth.
We've been talking about some pretty abstract stuff. Why should we care about coding with shapes? What's the bottom line here? Well, the takeaway is actually pretty simple, but it's also profound. This big shift in perspective lets us build communication systems that are just fundamentally more resilient. By encoding our information in these larger, more robust mathematical objects, we can handle the noise and chaos of the internet in a way that just wasn't possible before. So the next time your video call is perfectly clear or you download a huge file without a single error, you can give a little nod to the elegance of Subspace Codes. It's that hidden mathematical engine humming away in the background, taking that chaotic storm of mixed up data and delivering your message perfectly. It really makes you wonder, doesn't it? We've already gone from points to shapes. What's next? What other beautiful, abstract idea is sitting out there right now, maybe on a blackboard in some university, just waiting to become the foundation for our next generation of technology? Something to think about. Thanks for tuning in.